Hello students. Today's objective will be 118. Students will be able to classify real numbers. Go ahead and get that down. Great. The first vocabulary word that we are going to learn today is rational. And what a rational number is a number that can be written as a fraction. Today we have a really special guest joining us.
I don't know why we're doing.
Okay, go ahead, Jen.
All right, so an irrational number is a number that cannot be written as a fraction. Help if I can spell. Some examples of irrational numbers are numbers like some square roots, the number pi, and we'll learn a lot about those later in the year. A natural number is a number that we think of when we count. Numbers like 1, 2, 3, 4, 5, 6, etc. Those are your natural numbers. Integers include these, but they also include the negative numbers as well, the negative natural numbers. So, for example, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, etc. In both directions. When we're asking about a square root, that's an operation that gets us thinking. For example, square root of 9 gets us to think, what number times itself would equal 9? Well, what is that? What times itself gives you 9? Yep, you got it. 3. Or, for example, if we were to ask about the square root of 25, what number times itself equals 25? Well, 5. Those are square roots. They're operations where you give a number and it spits out what number times itself equaled the number you started with. Perfect squares are numbers where you can take the square root and get a whole number. For example, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. So if we were to take any integer and square it, we should be able to get a perfect square. Maybe skip a few, but 6 times 6 is 36. And the idea is that you can take the square root of any one of these numbers and you'll get a nice whole number. Like the square root of 36 is 6. The square root of 9 would get you 3. Right? And while we're at it, we actually have some special symbols to show all the sets of rational numbers, all the irrational numbers, all the natural numbers, and integers. Some of them make sense, some of them don't make as much sense. For example, natural numbers, we can write with a fancy letter N. Integers, we use the letter Z, a script Z, to illustrate all the natural numbers, all the integers. Rational numbers, we use the letter Q, so it's a Q with an extra line on the end. And I don't believe we have a fancy letter for the irrationals, so we'll hold off on that one.
How about for real numbers?
Real numbers, and I'm guessing we've talked about them, real numbers, we use a script letter R. So real numbers will look like this.
Like Mr. Seela mentioned, you're going to get to complex and imaginary numbers in Algebra 2, but for now we're going to focus on real numbers. So the bigger umbrella is a real number. And a real number is also any number that lies on our number line. From there, we can categorize any real number as either rational or irrational.
We're going to start right here with the rational numbers. We'll work on categorizing rational in just a second, but it might be helpful to understand that it's actually pretty easy to identify when you have an irrational number. If you ever have pi, but pi is an irrational number, Now, it's not because of the symbol, it's because of the decimal pattern it produces. Pi is, I don't know if this pi is going to help me out, 3.14159.
926.
2 nines in a row? What? 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, 3, 2, 3, 8, 4, 6, 2, 6. You see, this goes on and on forever. If we look very carefully at this, I want you all to try to find a pattern. Like anything that would help you predict the next number. You should be a little bit confused because you can't do that. Nothing within this decimal pattern would help me just predict with complete confidence what number comes next. And that's what makes pi irrational. There's no way to make this into a fraction. There's no way to predict the next number in that decimal sequence. Same idea with the square root of a not perfect square. So if we had, like Mr. Seelan showed, the square root of 25, well that's 5. That's a whole number. We call it a natural number or an integer. But if we have the square root of a not perfect square, let's say 17, the square root of 17 is
4.123, 105, 625, 617, 661.
And realize these dots mean like this number will keep going on forever. Again, look at this decimal pattern. It starts 1, 2, 3, so maybe you're like, okay, 4 might be next. But if you look, at no point in time is it going to be obvious what value follows. And that's what makes it irrational. If you can't predict the next number in that decimal sequence, then you should say, oh, that's an irrational number. These are the two big categories right here. When you're working with pi, most things associated with pi are going to be irrational. And then the square root of a not perfect square. So again, don't confuse this. If we had the square root of 9, that's 3. That's a rational value. Like this doesn't even go over here. Anything that produces a whole number is going to be over here on the rational side. But these are the cases where you can identify, okay, I think I'm working with an irrational number by analyzing that decimal pattern.
So hopefully you're thinking that if we took that square root of 9 and we got an integer, it will be rational, also because we can write any whole number over 1, making it a fraction. So any integer or whole number is rational. That being said, not only whole numbers, but we can also have fractions, right? Improper or proper, or mixed numbers, but we don't generally like working with those. Any fraction. We should also know that fractions are simply decimals. So if we have a decimal, such as 0.7 or 7/10, we can rewrite that as 7/10. Because the decimal terminates, we can look at the place value and simply rewrite it as a fraction using that place value. Now, over here, Mr. Riggs mentioned, some decimals do go on forever. And they are irrational because there is no pattern. But if we look at a familiar decimal, such as 0.333, repeating, hopefully you realize that this is the same as 1/3. Now, although this is continuous, since it does have a pattern, it is going to be rational. Another example we could use is 14/99. Now, since it's written as a fraction, we know that this is rational. Let's go ahead and divide this and see what decimal we get. We should get 14.14, and the 14 repeats forever. Now, both of these are continuous, but since there is a pattern, or we are able to predict the next digit, it is also rational. And also, let's not forget our negative numbers. So remember, rational or irrational values, we can throw on a negative pi. We can throw on a negative radical 17. or a negative 14 over 99, they are still rational or irrational, and that's dependent on the decimal and not the regular consonant.
We're on page 41 right here, just to do a little bit of practice to make your homework hopefully a little bit easier. But right here, we have 2 7s. Before you do anything else, you should notice that's a fraction. That's what rational means. You can write it as a ratio. Fractions are ratios. So right away we know, yes, that's a rational value. The y is it's a fraction. Now it's really cool. We can even prove that with the decimal pattern. If you did 2 divided by 7 in this height,
0.285714. Repeat.
if you look at first, it might seem like, wait, I just see just a bunch of random numbers, but if you look really carefully right here, 285714, 285714, that pattern is going to repeat on forever. If you can predict the next value, if it's a repeating pattern, that makes it a rational value. Looking right here, this next one, and then you see a bunch of these decimals, but notice how this 4285571, that portion right here, it's also underlined up here. Those 6 numbers repeat on forever. So this is also a rational number. The reason why? It's a repeating decimal pattern. Right, this one's really fun and a little bit tricky at first. It's a fraction. So your brain might go to it's rational. But if you look at what's being divided, we have pi, which is at 3.14. But it's not just that, it goes on forever divided by 3. When we divide those quantities, we get
1.0471975551.
and on forever. If you analyze really carefully, you can tell it's pretty much impossible to predict what's going to come after that 1. You might guess and get lucky, but you couldn't predict the one after that. There's no pattern here, and that's what makes it irrational. The reason why? No decimal pattern. And even the word pattern implies I can predict what comes next. If there's no decimal pattern, I can't predict what's next, that makes it irrational. You'll see that anything you combine with pi plus a number, pi divided by a number, pi times a number, will always produce an irrational value. We're going to skip down to 927 divided by 930. Right away, you should see, okay, that's a fraction. I don't see the value of pi involved, so I know it's a rational value. And the reason, again, it's a fraction. But here's what's really cool. This is where you can be smarter than what your calculator shows you. When you divide these 2 quantities, you get
0.9967741,935.
and you get on forever. This is what your calculator is showing you, and if you just looked at this, you would probably say, well, it's an irrational value because there's no pattern there. The problem is your calculator gets bored and it just rounds, and it stops showing you all the values. If these values were to extend on forever, we would be able to see the decimal pattern. Like, it does exist. This would be really fun. If you went online and actually divided these, you'll see that decimal pattern if you divide these values like into Google. But right now, it looks like there's no pattern. But recognize it is a fraction, that makes it a rational value. Go ahead and finish whatever you were assigned to do in class, and we will practice more of this tomorrow.